Hello, this tutorial is entitled Statistical Modelling, Uncertainty and Sensitivity Analysis. First of all, it's useful to explain what we mean by sensitivity analysis and uncertainty. So sensitivity analysis is a very broad area. So when we're doing statistical modelling, we will often come across the term sensitivity analysis. And I think of this as being the overall overarching title that includes when we discuss uncertainty. I think when we think about sensitivity analysis, we can think about what if type questions. So for example, if we had multiple studies, we may say, what would happen if we excluded some studies, or perhaps if we excluded some subjects? Perhaps one study looked a little bit strange. We may wish to see the results with that study excluded. Similarly, we may wish to treat or impute missing data differently. So if some individuals, for example, didn't have any concentration measurements, we would want to impute those with the average for that dose, or perhaps we would want to do something else. Another example would be if we wanted to use a conservative estimate of the treatment effect. So rather than relying on the point estimate, we might want to look at the lower confidence interval or prediction interval and use that for predictions. For uncertainty, we can really think about parameter uncertainty, and here we can talk about more kind of objective measures. Perhaps some of those earlier ones are somewhat subjective decisions, but when we talk about parameters, we can talk about the relative probabilistic support for different values. So how one value is supported more by the data and another value is supported less. Similarly with models, especially if they're nested, we can talk about the relative support for one model versus another model. And the third section, which naturally doesn't have a home, is around design and the data. And this is important because it defines the model space and the parameter space. So we're going to talk mainly about uncertainty today and mention a little bit about sensitivity analysis. So why should we be interested in uncertainty? Clearly, all parameters from a statistical model are estimated imperfectly. It is clearly not wise to focus solely on point estimates of the parameters from our model. So if we have an ED50 estimated at 10, we would like to know if it's 10 plus or minus 1 or 10 plus or minus 10. That clearly has a big role in how confident we can be about the robustness of the results. So generally there is a goal to generate predictions which reflect our knowledge or equally reflect our ignorance appropriately. So here, for example, we have a simple just one parameter, and we can think of some values of that parameter as being best, so they're most consistent with the observed data. And we can think of some others that are perhaps plausible, more towards the extreme of the distribution, and we can think of some parameter values that are extremely unlikely. They're really inconsistent with the observed data. And of course this is a continuum, so we think these values are more likely and these values are less likely. Since we have many parameters, we will normally wish to integrate over the parameter space. So here, for example, we're showing the calculation for how more times that the best value here should appear relative to the plausible value, and how many times it should appear relative to the unlikely value. So this is about 7 times more likely than this type of value, and this is around 3,000 times more likely than this value. So when we do simulations, we would like to simulate across this distribution and actually get this relative weighting for the parameter values appropriately. Perhaps a typical view on uncertainty, so this is how I used to think about uncertainty 5 or 10 years ago. I would think that I had some data, I would have a model over here, and then I would estimate that model. So I get my estimated parameters, I get my estimated standard errors, and I get my estimated variance covariance matrix, and I could use this information here to go on and construct a prediction interval, like a 90% prediction interval here, for the shape of my dose response. So this can be seen as the following sequence. We're going from a data set, we're selecting out the data that we're going to model, we're going to use that selected data to generate a final model, and we're going to use that final model to go on to our predictions. Unfortunately, often a modeler will try numerous candidate models with the misguided goal of selecting just one. This mindset needs to change. So many of us will have been educated along the lines of testing a series of models and the idea that we would then select out the best one and show the results for that. And this is what this graphic is trying to illustrate here. we can think about this white box as being the model space, so the universe of all possible models we could have investigated. And this black circle in the middle represents the final model presented. But actually, around that, there are other very good models that are well supported by the observed data. This may have been the one that the analyst has picked out, but actually there's others very good models around that. And similarly, there's these defined here as intermediate models, where again there's some support from the observed data. And then at the bottom we have poor models. So this is little support from the observed data. So the data doesn't like this relative to these other models. These other models are actually considered better. So we may be interested to know more than just predictions beyond the final model here, and actually to know what was going on in some of these other models as well. Thorough overview is to start with the design. The design is going to be leading us to the data. The data is going to be selected out. So perhaps when we're doing this, we can think about last observation carried forward as one way of selecting out a data set to model, or we can be using the longitudinal data that's been collected throughout the clinical study, or we're analysing a single endpoint, a single efficacy endpoint, or we're modelling two efficacy endpoints simultaneously. So there's a selection here of the data. And here we're going through to select models, so the plural here. So we're not just thinking we're only going to select one model, but perhaps there's going to be a number of models that we're going to move forward and look at the results of those for the predictions, and then the predictions for these different models, and think about how they impact the decision-making process. Thus, there are three levels of uncertainty. We can think about at the lowest level, we can think about the relative support for the different parameter values for a given model and for a given design and data space. So this lives within the model space. So here's the model space, and the model space is our range of different models that we could be considering. And then the model space lives within the design and data space, because this is controlling the range of models that we can look at is dependent on the type of data that we have. So let's talk about the first of these, the parameter space. So parameter uncertainty simply aims to determine the relative support for the different parameter values across the multidimensional parameter space. So within a Bayesian framework, we would look to define a model, a likelihood and a prior with a maximum likelihood estimation. We just need to define the model and the likelihood. And really what we're looking to do here is to determine the support for different parameter values across the p-dimensional parameter space, if there's p parameters. So nice distributions look like this. So we just have our single distribution here like we showed before. Or perhaps when we have two parameters, we have the distribution for parameter 1 and distribution for parameter 2. And we're looking here at the joint distribution of these parameters. And here we can see that they're actually uncorrelated. However, in the real world, the joint distributions may well be asymmetric. So they may have a long tail. So we can think about transformations of our parameters, which perhaps improve the shape of this curve and make it more normal. The joint distribution of the parameters will also be correlated. So as one goes up, the other may go down, or the other one, as one parameter goes up, the other one goes up. So it could be a positive or a negative correlation between the parameters. And indeed, the joint distributions may be very ugly. So they may have plateaus, or they may have multiple peaks. So they could actually be quite unattractive. I think it's important to note that for the same data and the same model, there is still considerable heterogeneity in determining parameter uncertainty. So there isn't just one way of determining parameter uncertainty. We can get potentially different answers depending on how we do it. So we can think about estimating the joint distribution of the parameters using Monte Carlo Markov chain, so like the Metropolis-Hastings algorithm. And this really is the gold standard. It maps that complex joint distributions or p-dimensional distributions. Of course, maximum likelihood estimation is a very useful, quick, fast way of estimating our models. And we can use the maximum likelihood estimates and the variance covariance matrix to approximate the joint distribution of the parameters using the multivariate normal approximation. So we need to think about the parameterizations of why we would parameterize log ED50 rather than ED50, because the multivariate normal approximation is going to work better on that log scale than on the untransformed scale. Third point here is the recommendation: do not use a non-parametric bootstrap. The non-parametric bootstrap is ubiquitous, everybody likes to use it, but it's rubbish. It really doesn't generate intervals with the claimed coverage properties. I'm not going to go into that now, but my general recommendation is keep away from non-parametric bootstraps if you're interested in understanding uncertainty in parameter values. The results that we get are influenced by many factors. So for example, in Monte Carlo Markov chains, it's going to depend on the number of iterations, the duration of the burn-in, the number of chains, one chain or multiple chains, the thinning used. There's going to be numeric differences between what I might do and what you might do, even though we may be actually applying a very similar methodology, because we may be using different software. The software could be using different algorithms and different implementations. So especially for maximum likelihood estimation, you have things like adaptive Gaussian quadrature, you have first order conditional estimation as ways of trying to get around the integration of over the random effects and how it achieves that. We have different convergence criteria, and if you have systems of ordinary differential equations, you'd have tolerances associated with that. So even though you may be thinking that you're actually using a very similar model, you're going to end up with different results between the different softwares and implementations. I think it's worth noting that the quality of the multivariate normal approximation will depend on how well behaved the joint distributions are. And what I mean by well behaved, it's how well the second derivatives of the likelihood function at the maximum likelihood estimate approximates the full joint distributions. So over here we have two parameters which are uncorrelated, so we can look from the top here or looking from the side here, and in this case maximum likelihood estimation would do great, as would Monte Carlo Markov chain if we were trying to map this joint distribution. In this middle plot here we have a correlation between the parameter 1 and the parameter 2, they're positively correlated. And again, if we think about the shape of this joint distribution here, maximum likelihood will look at the rate of change as the top of this likelihood here to approximate this distribution, and it would do a great job, as would Monte Carlo Markov chain. But in this third example, here we have something that perhaps is often referred to as a banana-shaped joint distribution. And here, by going to the top of the likelihood function here and trying to approximate this, maximum likelihood estimation is not going to do a great job, but Monte Carlo Markov chain would do a great job. It would be able to describe this full distribution. I think it's important to note that when we incorporate uncertainty, predictions will be different and potentially curious for nonlinear models. So here's a simple example where we're just considering one parameter. So here we can think about the log ED50 being a value of log 10. So the ED50 here is about 10, yielding a result of around 0.5. And this is this black line here. However, if we think about what the simulation would generate if we took into account the standard error, so here there's a standard error on this ED50, and now we have 100 simulations with different values of the ED50, from low values of the ED50 through to high values. And if we average all these grey curves, we obtain the red line here. What you can see is that the red line, because it's a nonlinear model, is generating a different average prediction relative to the population prediction. So we may ask, which of these is right? Which is the better estimate of the average prediction here at 16 or at 32? And you can think about really, do I believe in a single value for a parameter, or do I think of a distribution? And I always think in terms of a distribution, so I would be naturally leaning towards the red, but we would need to make sure that this standard error is reliable, such that these simulations here are actually reliable by going towards lower values and towards higher values in this way. And you can think about how this type of simulation would affect predictive checks or posterior predictive checks. When I talk about predictive checks, the terminology is often used with perhaps where there's no uncertainty on the parameters. So if you were looking at how well your model performed relative to some observed statistic within the data, you might want to do a predictive check where you're not incorporating the uncertainty on the parameters, or you can do it where you do incorporate the uncertainty on the parameters, which is called a posterior predictive check, which is a well-used term in the Bayesian literature. So we've talked a little bit about parameter uncertainty. Now let's talk about model uncertainty. So when we think about model uncertainty, we can ask, why did the analyst only show the predictions from their final model? And how are we supposed to judge this? So here we have our analyst 1. They've selected a dataset X that they're going to model. And here we see that they've done 55 potentially different models. And they've come up with this final model here. Perhaps along the path to this, there were other good models. And perhaps there were some intermediate models. And perhaps the starting models were very poor. So I'm not so interested in seeing these models, because these are clearly inferior to these ones. But perhaps these ones are interesting. So model building and the impact on predictions. I think transparency here is the key word. Model building is a good thing. We should interact with our data. However, it's important that we understand that we're all capable of modeling fails. That is, being misled into believing artifacts in the data are real. So if we see that our drug, the Emax, looks a little bit higher than the other drugs in the class, we may be tempted to believe that, but actually we could be wrong, and perhaps we should be setting the Emax at the value of the other drugs in the same class. Model building is subjective, so whilst there's a lot of objectivity in model building, there will always be a degree of subjectivity, and it can be very tricky. For example, the analyst fixes some parameters. Perhaps some models do not run. I think it's important to show these to the reader and tell the story. I think there's often a conflict between the models we would like to fit and the strength of the data at hand. So here I make the point, did you do a clinical trial simulation beforehand and a simulation re-estimation step to see how well your chosen model would do on a data set like this? Because that's what you're trying to convince yourself, is that these estimates are sound and reliable. In reality, if you work within the pharmaceutical industry, you can think that there actually may be multiple analysts using different data sets and different models. Clearly, these results should be shown together. So here we have analyst 1, so we could think of this as the biostatistician working with LOCF. The analyst 2 could be the PK/PD modeler looking at maybe one endpoint or two endpoints. And perhaps there they have a range of models, and up here they have a range of models. And typically we see this in one report and this model in another report. I think most importantly, how would the key decisions, for example dose selection if this was a phase 2 study, how would dose selection in phase 3 compare across these models? And really we would be interested to look across this whole range of models here, and not just the last one, because all of these are competing models. And just because the data isn't strong enough to differentiate between them doesn't mean that the modeler should just select one of them. And similarly down here for this analyst, they have a range of competing models. And the key question at the decision point of view is, are these important differences? If we look at the results across these 6 or so different models, and they all look very similar, and the dose selection looks very similar, we don't need to worry about trying to differentiate which model is the best one. But if they're giving different results, it's important that we know that. It's just one slide here just to mention that when you do have multiple models, you can look to just integrate them into a single value. You can Google Bayesian model averaging. Personally, if there's 6 or 7 different models, I would like to see at least at the first step the results of those 6 or 7 separate models before we start trying to integrate them into one single prediction. The highest level, we have the design and the data. The reason this is important is this controls the model space, which in turn controls the parameter space. I'm using the term uncertainty here, but you can be flexible with that wording. But I think it's often overlooked. The importance is that the data that you have controls the model space. So the types of models that you can look at is controlled by your data set. So here, for example, we have the situation of in pharmacokinetics where we perhaps have rich sampling. So we have a number of 6 subjects here when we're just showing that if they got sampled at 24 hours and at 12 hours, at 6 and 4, quite a lot in this early absorption phase, versus perhaps sparse sampling where there's only one measurement at 4 hours and one measurement at 24. So we can ask, what effect will each have on the estimated absorption parameters and associated inter-individual variabilities, for example a first order process Ka or the inter-individual variability on Ka. So here for this very simple absorption model, this rich strategy and this sparse strategy would both give reliable estimates of Ka and the IIV on Ka, but what would happen if we had a much more complex absorption process? And it's important to understand that the estimates we get are always conditional on the data at hand. They are not necessarily the truth, so they may well be biased. For example, if there's very little data in the absorption phase and you have a very complex absorption process, then the IIVs on some of these absorption parameters may go towards zero, simply because the likelihood does not want to pay the penalty of a non-zero random effect unless the model fit is improved by including it. So when you have lots of random effects, if it can do a good job of describing your few data points here, so like here, just 1 point here and 1 point here, it doesn't need lots and lots of random effects in the model to go through these points. So whereas here, when you have lots of data in this absorption phase, it would want those extra random effects in there to describe the profiles that we're seeing. Another example is how the data that you have controls the model space. So if we think about model-based meta-analysis, so the idea here is that we're bringing together lots of different studies and we're combining them to try to get an overall estimate of the drug effect from smaller studies through to larger studies. And in that type of meta-analysis, you can estimate the inter-study variability in the drug effect. And this will typically not be zero. So the variation we see between studies is bigger than we would expect just by chance. Now if we contrast that with a phase 2 study analysis, we have a single study, we can estimate the drug effect from that single study, but it essentially is implicitly assuming that the inter-study variation is zero, because if we just used that point estimate from that study and the uncertainty around it, it doesn't reflect the fact of what we see up here with the meta-analysis, where we do see inter-study variation. So if we're planning a phase 3 study with a new treatment from a single phase 2 study to a gold standard, which is based on a meta-analysis across multiple studies, what inter-study variation should we use to predict phase 3? So here again, if we have a single study, we tend to be quite happy to ignore study-to-study variation, but if we have multiple studies, we know it exists. So it's important to understand that if you have multiple studies, you can estimate something, but when you have a single study, just because you can't estimate it doesn't mean it's not there. I think for the design considerations, as a general rule, spend at least as much time designing a study as you do analysing the study. So for example, how did you decide what dose range or regimen to study? How did you decide the number of subjects per dose and regimen? How did you decide the duration of the study? How did you decide the number of observations? How did you decide the timings of the follow-up visits? How precise, on the basis of this observation schedule that you've suggested, how precise were your models, your PK/PD models or your stats models are going to be able to estimate the drug effects? Also, what models are you going to be using? So for example, will the data be able to clearly differentiate if you have, for example, BID dosing, twice daily dosing versus single, once a day dosing? How are you going to differentiate between whether your drug in phase 2 with a BID regimen and a QD regimen, should you go into phase 3 with the BID regimen or with the QD regimen? Is your data going to be strong enough to be able to detect differences between those two regimens? Similarly with covariate effects. So rather than just to wait till you get the data and see if you can detect covariate effects before you've even run the study, you'll have a good idea by doing clinical trial simulation as to whether you can actually estimate these things well, because that's really the critical thing here. If there are models that you're interested in estimating, make sure the data that you're going to use is actually capable of estimating those interesting models. And that's really what this bottom point is reiterating here, is we often have an idea of the models that we would like to fit to the data and differentiate between these models versus the actual data that we get, which could be very noisy and quite weak across a limited dose range. And then actually, are you going to be able to answer those interesting questions? So really, if you do that all at the design stage rather than waiting for the analysis stage, to realize that you actually couldn't differentiate between these important models. Finally, it's worth mentioning about sensitivity analysis. The main thrust of this tutorial has been on talking about the uncertainty side of things, but it's worth mentioning and giving an example of a sensitivity analysis. Our starting point is that all models can be criticised. So I think a healthy skepticism is good, but being just negative is bad. So it's easy to try to find faults in a model, but actually if you understand why you're trying to investigate that and to see what you would need to understand whether that model is actually generating useful results or not. And I can think of 3 audiences that you're interested in convincing. First of all is yourself. So if you're analysing 2 endpoints together, or perhaps what are the results if you analysed each endpoint separately? Or perhaps if you were bringing together multiple studies, again, what would happen if you left out that study with a very large treatment effect? Does it change some of your decisions? Similarly, you can think about your colleagues in the company, so they need to buy into the fact that your model is actually doing a good job, or your models are doing a good job. And similarly then the wider world, so the regulators and the payers who are going to be looking at the results from your modelling and convincing themselves that it's reliable. And over here you can think about as you go down from yourself through your colleagues to the wider world, there's more heterogeneity between the individuals in terms of their background. Perhaps there's increased skepticism around modelling. And here I'm talking about increasing personal risk, primarily because they're further away from the work than yourself. Obviously, if you do bad work, it's going to reflect badly on you. But actually, in terms of these people making decisions on the basis of it, you perhaps are very comfortable doing it because you did the work, but they're actually quite far away from it. So it's important to understand that they're going to look at your modelling work through a different pair of eyes than you would. I think the key question for the modeller is, do the choices that you made, so your data selection and your model, significantly influence the key results in the decisions? And the key thing to understand there is that a significant effect on the results isn't statistical significance. So if you're looking for the interaction between 2 drugs, just because you can't detect that there's a clear interaction between the 2 drugs doesn't mean it's not there. And the regulator may want to see the results when you look at different types of interaction models between different drugs to try to understand, are they making a good decision or a bad decision on the basis of this data, rather than allowing the modeler just to select one model and show them the results to that. So here's an example. In this situation, we were using a phase 2 dose response study, and we were interested to look at the probability of success in phase 3 following the phase 2 study for sample sizes from 100 per arm through 200, 300, 500 and 1,000 patients per arm in a head-to-head versus placebo. Metric of success here in this example would be the primary efficacy endpoint, which was to get a significant result for the stats test versus placebo in phase 3. And as you see here, as you go across the dose range, you're more likely to get a significant effect because the treatment effects are getting bigger, the underlying treatment effects are getting bigger. And here, the sample sizes are also getting bigger. And we're showing the results for one model and for a second model. And rather than just decide on a single model that we liked, we may want to show the results across 2 models or 3 models or 5 models to see if the decisions that we're going to make are sensitive to the model choice. So here, for example, at 8 milligrams with 300 patients per arm, we can see that the 2 models are somewhere between 70 to 80% probability of success. However, what we also did with this project was we looked at worst case type scenarios under model 1 and worst case scenarios under model 2. So this is where we took the distribution of the treatment effect, and rather than use the whole distribution of the treatment effect to predict what was going to happen in phase 3, we looked at the lower end, so at the more negative side of the prediction of the size of the treatment effect, to see whether in that situation whether the phase 3 study would be successful. And we obtained these 2 extra curves conditioning on the 2 different models. And what we can see here is before, when we were looking at our model 1 and model 2, we could see that we were up at around 75-80% for model 1 and for model 2. But the sensitivity analyses, where we're a little bit cautious, come all the way down towards 50 and maybe 60 something. Whereas with n equals 500 per arm, we see that the model 1 and model 2 are both giving very high probability of success in phase 3. But even in the worst case scenario, with 500, we're still looking like we're going to have a successful outcome. So rather than just focusing on n equals 300, perhaps we're prepared to go up to 500 if we want to be sure to have a good outcome in phase 3. So, as a summary, at the design stage, we need to investigate and understand how different candidate designs will allow models of interest to be estimated and discriminated between. So we're bringing, before we've even collected any data, we start thinking about the models that we're going to want to estimate and how well they're going to be estimated and how well we can discriminate between them by making reasonable assumptions about the drug parameters. And then at the analysis stage, we need to recognize and show that the key results are incorporating both parameter uncertainty. My advice would be to learn Monte Carlo Markov chain. Many of us would have grown up within a point estimate and standard error world, but actually Monte Carlo Markov chains and mapping the joint distribution of the parameters is the future, and as the computers get faster and faster, that's what we're going to be doing a lot more of, so I would encourage you to learn that. We also need to think about, when we're presenting the results, showing the results across model uncertainty, so being prepared to show the results across different models to see if the results are consistent or inconsistent between the different models, and also including more sensitivity analysis. And as always, to have the key results and the decision part of the process central to the design and the analysis process, so ensuring that the study can answer the question. I hope you found this video interesting. If so, you may want to check out our other videos. If you have any comments or suggestions, please feel free to contact me.